All right, so this is the Project 2 demo done by Team 10. I'm Alex Van Handel, but you'll also hear from Kara, Avery, and Stephanie later on in this presentation. All right, so what is some of the motivation for image processing? Well, a definition is it is a method to perform some operation on an image in order to get an enhanced image or to extract some useful information from it. But a more accurate definition is that it is a means of translation between the human visual system and digital imaging devices. So basically allows for machines to see what the human sees and can put that into information and other data. And what's really cool about this is that it has a huge range of possibilities and applications. It can range from medicine to entertainment to geological processing and also to remote sensing in other areas. So what is happening in the world of image processing right now? Well, currently it is being used in the medical field and also within the biomedical field in engineering. It can be used in X-rays, MRIs, and CAT scans, and etc. And so this allows for doctors to hone in on certain areas and can detect things like tumors, broken bones, stuff like that, and just allows them to get better diagnostic of what is happening in the human body. Also, it can be used in AI. Computers can recognize human faces, and this is kind of how your iPhone works to uses facial recognition to unlock their phone, right? It can recognize your face and therefore unlock your phone, and it just helps with like security reasons and making sure like you're the only one that can get in your phone. And it's also used in computer graphics. Just helps to model the real world and makes it a lot more precise, like in CGI and that type of graphical stuff. So it's also used in UV imaging, and basically there's a satellite way above the Earth, and it can scan the ground and analyze information from this. And this is pretty cool. One application that can use for this is during an earthquake, it can detect damaged infrastructure and actually send that data to Earth, and that just helps, like rescue teams find areas where they might need to go and see if anybody's been injured, and just helps those type of rescue teams.
First, I'll start by demonstrating how the code error detects or checks for errors when you're typing in the input file. So I'll type coin, and the file you have typed is not a PNG file, then something like coin PNG. So it is a PNG, but no image is found under that name. Then I'll type the correct name, and it starts processing. So we have a timer here that tells you how long it took for each process, and I'll give a short explanation of what each process is. So first we have the program asks for the PNG file here, and then it checks for errors and inputs the image, and then the processes of grayscale, kernel processing, edge blurring, edge enhancement, and thresholding process. And then we have where the program outputs and saves the image, and the timer. And then up here you can see the plot of the final image.
Okay, so the grayscale function, this function will convert the red, blue, and green pixels to grayscale and then outputs a 2D array of the grayscale values. So this is pretty standard. In the second line of the function, we're just going to start our timer. Then the third line, this is accessing the RGB columns. So we're going to get the RGB values for each pixel, and then the next line we're going to multiply the RGB values with their corresponding weights to convert it to the grayscale. And then we're just going to end the timer and find the time elapsed and then print that.
So for our next two operations, noise reduction and edge detection, we're essentially doing the same thing. We're taking a kernel and running the image through it to process it. So while we could write separate functions for each of these, it would be nice if we could just have one general kernel processing function. And that can work for any size kernel and any size image, with the only assumption being that the window or kernel is odd and square, so that we can have that central element. And there's three main problems that arise from this, and that's avoiding reference errors, accessing the pixels around the central element, and the actual math, which is the convolution. So for avoiding reference errors, this is just a matter of when the central pixel is around the edges of the image, and it's trying to reference things that are outside, the elements that are outside of the image. We can fix this by padding. So here's kind of a simple example where we have a 2 times 2 padded with zeros, 2 times 2 all around, and we're basically taking that principle and applying it on a larger scale. But again, we're using variables that describe the dimensions of the kernel so that we can adapt to different sizes. Our next problem is actually accessing the pixels that we want, so the pixels around that central pixel. And we have to do this without hard coding. So early in the coding process, we talked about how if we had a set, say 3 by 3, we could just assign it manually. So we would have the window, 1, 1, which is a central element, equal to the image ij in the for loop, the 0, 0, I minus 2, j minus 2, and so on, and then sum all of the kind of referenced image element indices or elements together. But this doesn't work if the size of the kernel changes. You'd have to rewrite the entire thing. Instead, we use this little formula, and it would take a bit too long to explain, but it again is adjusting based on the length of the kernel and the element in the window. So the third part is the actual math, the convolution, and it's very adequately named because it's a convoluted process. Instead of associated element multiplication or even just general matrix multiplication, I like to call it a zigzag multiplication, where you're kind of going back and forth between the corresponding different rows and columns. I believe they described it as if you flipped the rows and columns, you would then do corresponding element multiplication. There is a way to access what element you need to multiply in the other matrix though, and that is by taking the dimension of the matrix, -1, since referencing starts from 0, and then subtracting the original matrix index. And that's kind of what we've done here. And this works because both we're calculating the sum, and both multiplication and addition are commutative. So here's kind of our general kernel processor in full, and it's a bit long, but again, we kind of we sacrificed simplicity for robustness and flexibility. And so now it's just a matter of plugging in the right kernels. So for our noise reduction, this is the 5 times 5 Gaussian blur kernel, which is shown here. And while this isn't the full function, we have a few more lines about calculating the time. The meat of it is just calling that kernel processing function. Similarly, for our edge detection, this is just passing the syllable x and the syllable y both into the processing function, and then calculating the gradient using the equation shown here, and going through each pixel as we do so. And that outputs the edge.
So the thresholding function is the function that will threshold edges of the image array to create greater contrast by setting all pixels to black or white depending on if they meet a certain threshold. So the threshold we used was, the threshold cutoff value was 100. This was just because higher values didn't really show as much detail. Then the next line is initializing the final matrix. As for the for loop, this means that for pixels above the threshold, we're going to set it equal to 255, which will be white. And then if they're below the threshold, we're going to set it equal to 0, which would be black. Else the pixel is equal to the threshold. And then stop timer and find the time it took to complete, and then print.